23rd March 2005, 1:20 in the afternoon. Inside the distillation tower at BP's Texas oil refinery, the hydrocarbon level was rising. The furnace burners were continuously heating the feed. Under normal conditions, this heated hydrocarbon stream enters the tower where the lighter components vaporize and rise upwards, while the stabilized liquid product leaves from the bottom and moves towards the gasoline blending pool. But since the previous night, the feed has been entering the tower as expected, while the output was not leaving properly. The tower continued to fill, but the level transmitter was giving a false reading. Under normal conditions, when the hydrocarbon level reaches 7 feet, the instrument shows a 100% reading. But that night the level had already reached 13 feet, while the meter was still showing only 96%. The pressure control valve at the top of the tower was also not functioning properly. During the morning shift change, the operator did not know that not only the tower but also the heat exchanger and connected piping had become completely full. By 1:04 in the afternoon, the 170-foot high tower had filled to almost 158 feet, yet the level meter was showing only 78%. From outside, the tower appeared normal, but when the internal pressure exceeded the safe limit, the relief valves opened. Within just 6 minutes, nearly 196,500 liters of hot, flammable hydrocarbons flowed into the collection header. This material was supposed to return to a closed-loop system, but instead it reached the blow-down drum. The drum could not handle the pressure, and hydrocarbons began escaping through the vent. As the hydrocarbons escaped, their vapors formed a cloud and mixed with air, creating a fuel-air mixture that was ready to ignite. Around 25 feet away from this vapor cloud, a diesel pickup truck was reversing with its engine running. The hydrocarbon vapors entered the diesel engine. Unlike a petrol engine, a diesel engine does not use a spark plug. As soon as these vapors entered the engine, it began running uncontrollably, which could create a backfire or another ignition source. The ignition source ignited the vapor cloud, triggering multiple explosions in sequence. The cloud affected an area of almost 200,000 square feet. More than 18 people were killed, and around 185 were injured. Now let's look at the refinery as a complete system. A refinery contains multiple towers because crude oil is processed in different stages, using high temperature, pressure, and vacuum. Crude oil is mainly made of long hydrocarbon chains, but it also contains impurities such as sulphur, nitrogen, and metals. Different refinery units separate, clean, and convert these hydrocarbons into useful but highly flammable products. An oil refinery does not produce only petrol and diesel. It produces many different materials, so we can think of refining as the process of separating the hidden resources inside crude oil. After crude oil reaches the refinery through a tanker, it is first stored in large storage tanks. The process of crude oil extraction has already been explained in detail in a separate video. From the storage tank, the crude oil reaches the crude charge pump. This pump draws the oil from the tank and sends it to the heat exchanger train, where multiple heat exchangers are connected in series. Inside the heat exchangers, crude oil flows through the tubes, while hot process streams flow around them. These hot streams transfer heat to the crude oil and gradually raise its temperature. We will understand the source of this heat later. Crude oil contains impurities such as water droplets, salts, sand, and sulfur compounds. These must be removed because they can cause corrosion in pipelines, blockages inside the furnace, and damage to catalysts. The crude oil then enters the desalter. Here, water is mixed with the crude so that the salts dissolve into the water. An electric field is then applied, causing small water droplets to merge, become heavier, and settle at the bottom. This salt water is removed from the bottom, while the cleaned crude is sent forward from the top. After desalting, the crude oil again passes through the heat exchanger train, where its temperature rises to approximately 180 to 200 degrees Celsius. At this temperature, some lighter components can be separated from the crude. So the stream is sent into the Prefractinator. At this temperature, the lighter components vaporize, rise upwards, and pass into the condenser. This section mainly collects fuel gas, LPG, and Naphtha. The condenser cools the vapors and turns part of them into liquid. In simple terms, it removes heat from the vapor stream, with the hot vapors flowing through the tubes and cooling fluid flowing around them. After cooling, part of the vapor condenses into liquid. But LPG and naphtha still remain mixed and do not meet market quality standards. This mixture is then sent to the accumulator, where the liquid settles at the bottom. A portion of this liquid is returned to the Prefractinator, and this is called reflux. The gases remaining at the top of the accumulator are sent to the stabilizer column. A reboiler is installed near the bottom of this column, where high-temperature steam flows through the tubes and supplies heat. Because LPG and fuel gas are lighter, they move upwards, while stabilized naphtha is collected from the bottom. This naphtha is later upgraded into petrol. In simple terms, it is an early-stage petrol range stream. Later we will see how this naphtha is converted into petrol. After this, fuel gas and LPG are sent under pressure into the de-ethanizer column. Heat is supplied from the bottom reboiler, allowing the LPG and lighter fuel gases to be separated further. The LPG obtained from this section is not directly ready for sale, because it may contain hydrogen sulfide, mercaptans, and other sulfur compounds. LPG mainly contains propane and butane range components, which can be separated using depropanizer and debutanizer columns, depending on the refinery design. After this, impurities are removed through treating, drying, and testing stages to produce sweet LPG, ready for storage and sale. The Prefractinator separates only about 5 to 10% of the material from the crude oil. The remaining crude then passes through the heat exchanger train and enters the furnace. These heat exchangers reduce the load on the furnace by preheating the crude as much as possible before it reaches the furnace. Inside the furnace, powerful burners raise the temperature of the crude oil. By the time the crude leaves the furnace, its temperature reaches approximately 350 to 360 degrees Celsius. It then enters the Mainfractinator, also called the crude distillation unit, which is often considered the heart of the refinery. At the bottom of the Mainfractinator, the crude enters the flash zone. Because the oil is extremely hot, the lighter components vaporize and rise through the tower. Inside the tower, multiple trays are installed, with liquid collected around them. Let us assume that the liquid on one tray is at 310 degrees Celsius. If the boiling point of a vapor molecule is higher than 330 degrees Celsius, it cools as it contacts the liquid and condenses on the tray. But a vapor molecule with a lower boiling point does not condense on that tray. It remains in vapor form and continues moving upwards. In this way, different fuel streams are collected in different temperature zones. In the distillation tower, the lightest gases rise to the very top, while heavier products are collected lower down. Fuel gas and LPG are obtained from the top section. Naphtha below that, kerosene and aviation turbine fuel from the middle section. Diesel and light gas oil below that, followed by heavy gas oil. And finally, residue from the bottom. A crude distillation tower can be approximately 150 to 200 feet high and may contain around 30 to 50 trays, where different products separate according to their temperature ranges. During distillation, some heavier molecules may move above their correct tray and reach an upper section of the tower. To improve separation, some liquid from the upper tray is sent back down. This helps the heavier molecules settle lower, while the lighter molecules continue moving upwards. Sometimes lighter molecules such as kerosene can also come out with diesel. These lighter components must be separated from the diesel stream. For example, diesel is sent into the side stripper, where superheated steam is injected. This causes the lighter molecules to vaporize and move upwards, after which they are returned to the distillation tower. In the same way, every major product stream has its own stripper. However, the fuels obtained from this stage still do not meet market standards, so they require further treatment. In the Prefractinator, we saw that fuel gas, LPG, and naphtha from the top section are sent to the condenser. Similarly, the overhead products from the Mainfractinator are cooled and sent to the overhead accumulator. From there, a portion of the cold liquid naphtha is returned to the top of the tower as reflux. This cools the heavier components and sends them back down the tower, improving the quality of separation. Around 30 to 40% of the crude remains as residue at the bottom of the Mainfractinator. This residue contains very heavy hydrocarbon molecules. Processing it is challenging because excessive heating can convert it into coke. However, it still contains valuable oil molecules and trapped gases, so further treatment is necessary. Therefore, the residue cannot simply be heated further. The solution is to reduce the pressure, because when pressure decreases, a liquid boils at a lower temperature. For example, water normally boils at 100 degrees Celsius, but under low pressure, it can boil at a lower temperature. After the Mainfractinator, a residue pump sends the residue towards the vacuum furnace. A steam ejector is installed in the vacuum system to help create low pressure. High-speed steam passes through the steam ejector, creating a vacuum through the Venturi effect. Because of this vacuum, the residue can boil at a lower temperature before entering the vacuum distillation unit. A condenser is installed at the top of the vacuum distillation unit, with the vacuum receiver on the side. The steam ejector creates a vacuum in the receiver, and this vacuum reaches the tower through the condenser, reducing the internal pressure to approximately 10 to 15 mmHg. Compared with normal atmospheric pressure, this shows how intense the vacuum is. Vacuum towers are usually wider because as soon as the residue vapor enters the flash zone, they expand rapidly. These vapors rise upwards and come into contact with the cooler liquid flowing down from above. Heavier molecules that have vaporized unintentionally condense in this liquid and settle back down, while the lighter vapors continue moving upwards. Inside this tower, the lighter molecules move upwards and are called light gas oil. The heavier molecules settle towards the lower section and are called heavy gas oil. Because both streams come from the vacuum unit, they are collectively known as vacuum gas oils. The vacuum tower contains structured packing, which helps reduce pressure drop. Its internal tray design is also different, and nozzles are installed in different sections. When heavy molecules collect in these sections, they are drawn out and can later be converted into petrol and diesel range products. However, some molecules are so heavy that they settle below the trays. These bottom molecules are called vacuum residue. The vapors rising upwards are cooled in the condenser and converted into liquid. A portion of this liquid is sent back from the reflux drum to the top of the tower, while the remaining portion is drawn out as product known as light gas oil. Vacuum residue is not considered waste because it contains very long and complex hydrocarbon molecules. For example, the molecular weight of asphaltenes can be approximately 3,000 to 5,000. Therefore, this residue also undergoes further treatment, but through a different approach. The products obtained so far do not meet market standards because the distillation units have only separated hydrocarbons according to their boiling ranges. To turn these streams into final fuels, chemical treatment and conversion are still required. Now we will gradually convert these streams into usable products and move toward the final fuel stage, while understanding how the different units are connected. First, let us look at the streams that have come out of the refinery so far. The Prefractinator produced LPG, fuel gas, and Naphtha. The Mainfractinator produced fuel gas, LPG, Naphtha, kerosene, aviation turbine fuel, diesel, heavy gas oil, and residue. Vacuum distillation produces light vacuum gas oil, heavy vacuum gas oil, and vacuum residue. We will return to vacuum residue later. First, let us start with the heavy gas oils. The heavy gas oils obtained from vacuum distillation and the Mainfractinator can be combined and upgraded into petrol and diesel range products. Many impurities have already been removed, but these molecules are still present as long hydrocarbon chains, so they must be chemically cracked. In general, the better the hydrogen to carbon ratio in a hydrocarbon molecule, the better the fuel quality is considered to be. Methane, for example, has 4 hydrogen atoms for 1 carbon atom, which is why it is considered a clean-burning fuel. There are 2 main methods for upgrading heavy gas oils. The first is the fluid catalytic cracking unit, commonly known as the FCC unit. Inside an FCC unit, there is a long vertical pipe called a riser. Vacuum gas oil and heavy gas oil are introduced from the bottom of this riser through nozzles. Hot catalyst enters the riser through a side pipe. This catalyst is a fine powder similar to clay, and it remains at a very high temperature. As soon as it comes into contact with the heavy oil, the oil rapidly begins to vaporize. This reaction is extremely fast. Within just 2 to 3 seconds, the vapors can travel almost the full 25-meter height of the riser. As soon as the vapors reach the top of the riser, the catalyst must be separated from them. For this, an umbrella-like structure and cyclone separators are installed at the top. The heavier catalyst particles strike the wall and fall down, while the lighter hydrocarbon vapors continue moving upwards. During this cracking reaction, long hydrocarbon chains break into smaller molecules while carbon deposits begin to build up on the catalyst. To make the catalyst active again, it is sent to the regenerator. In the regenerator, hot air is passed through the catalyst, causing the carbon deposits to burn away. The regenerated hot catalyst then returns to the riser, and this cycle continues. The hot flue gas leaving the regenerator contains a large amount of heat. This heat can be recovered to produce steam, generate electricity, or support other heat recovery systems. In the FCC unit, hydrocarbon chains break into smaller molecules, but the product still comes out as a mixed stream. To separate these products, an FCC fractionator is used, where different streams are collected on different trays. Fuel gases come out from the top of the FCC fractionator, and these can be used for furnace firing within the refinery. LPG also comes out with them, and it is separated through a gas separation process, similar to the one used in the Prefractinator section. The naphtha coming out of the FCC unit belongs to the Petrol family, where the octane number is extremely important for fuel quality. The octane number indicates how well petrol can resist knocking inside a petrol engine. If petrol ignites by itself under piston pressure, knocking occurs and the octane number is considered low. But if the petrol ignites only through a spark plug in a controlled way, its octane quality is considered better. FCC naphtha has a higher octane number than natural naphtha, so it is a valuable stream for petrol blending. However, it can also contain higher levels of impurities such as sulphur and olefins. So it is sent to the gasoline desulfurization unit, where the petrol range stream is cleaned. How much petrol range product comes out of the FCC unit depends on the unit's yield. For example, if the yield is 50 to 60%, then approximately 50 to 60 liters of petrol range product can be obtained from 100 liters of feed. Light cycle oil comes out from the middle section of the FCC fractionator, and it belongs to the diesel family of products. However, its diesel quality is relatively weak because the cetane number is extremely important for diesel performance. To produce better quality diesel, the refinery uses hydrocracking. The hydrocracker is one of the most important units in a refinery. The feed for the hydrocracker also comes from heavy gas oils. Before this feed enters the reactor, hydrogen is mixed with it. The feed and the hydrogen mixture then passes through a heat exchanger and furnace before entering the reactor, where cracking takes place over fixed catalyst beds. Hydrocracking takes place at very high pressure, up to approximately 160 kilograms per centimeter square. Under these conditions, impurities such as sulfur, nitrogen, and oxygen are removed, while long hydrocarbon chains break down into cleaner paraffinic molecules. This is why the diesel produced here is cleaner, has a better cetane number, and can meet modern emission standards, fuel standards. The product leaving the reactor is still in vapor form, so it is sent to a high-pressure separator where unused hydrogen is separated and recycled. After the separator, the main product stream is still at high pressure. Therefore, before the pressure is reduced, it can be passed through a turbine to recover energy. The product stream is then sent into the fractionator. Light naphtha comes out from the top of the hydrocracker fractionator, but its octane number is low. Below this, heavy naphtha is drawn out, followed by kerosene, premium diesel, and unconverted gas oil from the bottom. This unconverted gas oil can be recycled back into the reactor or used later for lube oil production. So far, the hydrocracker has produced a comparatively clean diesel stream. The naphtha from this unit is also cleaner, so these streams are sent to their respective blending pools. Now let us collect and understand the streams coming from the remaining units. First, let us look at naphtha. It belongs to the Petrol family, but it is not yet finished petrol. Naphtha is obtained from units such as the Prefractinator, Mainfractinator, FCC unit, and Hydrocracker. The naphtha from the Prefractinator and the Mainfractinator is collected and sent to the stabilizer column. In the stabilizer, heat is supplied through the reboiler, causing lighter components such as LPG and fuel gas to come out from the top, while stabilized naphtha is obtained from the bottom. However, this naphtha may still contain sulfur compounds, so it is sent to a hydrotreater for sulfur removal. A hydrotreater is also a reactor-based unit, and its working is similar to a hydrocracker. Naphtha and hydrogen are mixed and sent through a heat exchanger and heated into the reactor. Inside the reactor, hydrogen reacts with sulfur to form hydrogen sulfide. The stream leaving the reactor then goes to a high-pressure separator where hydrogen is separated, and the naphtha is sent to the splitter column. Heat is supplied to the splitter column through the reboiler. Light naphtha comes out from the top, while heavy naphtha comes out from the bottom. H2S, light hydrocarbons, and small amounts of LPG and fuel gas also come out from the top section, and these streams are handled after treatment. Light naphtha is sent to the isomerization unit. Here the molecules are not broken. Instead, straight-chain molecules are converted into branched molecules, which improves the octane quality of the petrol range stream. This is also a reactor-based unit, where hydrogen is sent into the reactor along with the feed. The reactor outlet is then sent to a separator or distillation column to separate the isomerate. A stripper may also be used for better cleaning, and the final product goes to the gasoline blending pool. The incident explained at the start of the video was connected to this section. Hydrocarbons kept accumulating inside the distillation tower. The material in this section was relatively clean and highly flammable. Feed was entering the tower, but the output was not leaving properly. When the tower overfilled, hydrocarbons escaped from the system, leading to a major explosion. Heavy naphtha is treated in the catalytic reformer. Here too, the octane number of naphtha is improved through a reactor-based process. Several separators are installed throughout the naphtha processing section. First, light and heavy naphtha are separated. Then, additional separators are used in the isomerization and reformer units. Small amounts of light gases such as LPG and fuel gas come out from their top sections. These are sent to the gas treatment section explained earlier, where useful gases are recovered and waste gases are safely handled after treatment. The naphtha obtained from the FCC unit is cleaned in the gasoline desulfurization unit. It contains olefins, which help improve the octane number of the petrol range stream. Here too, the naphtha is cleaned through a reactor-based process. Finally, the products from all treating units reach the blending pool. Here, heavy naphtha, light naphtha, and streams from different units are collected. According to market demand and the required fuel specifications, these streams are blended to produce the final petrol. In the same way, separate hydrotreating units are used for kerosene, aviation turbine fuel, and diesel. In these units, impurities such as sulphur are removed through a reactor-based process, and each product is prepared according to the required fuel specifications. The basic working principle of hydrotreating reactors is almost the same. The main difference is the feed stream and the final product requirement. Now, one important stream still remains: vacuum residue. Its further treatment is carried out in units such as vis braking, delayed cooking, and solvent deasphalting. These processes can produce final materials such as bitumen, asphalt, and road construction products. Apart from petrol and diesel, a refinery also produces engine oil, lubricating oils, waxes, oil-based paints, and plastic-related raw materials. Many raw materials used in cosmetics are also connected to refinery and petrochemical chains. This video has been prepared after detailed research. If you have reached the end, please write in the comments which part of the refinery process you found most interesting. For more detailed engineering videos like this, please subscribe to the channel. Thank you.